Okay, good morning, afternoon, or evening, everybody. Welcome to the Explore NASA JEDI Aboveground Biomass Dataset Services and Tools at ORNL DAAC Earthdata webinar. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Daylight Savings Time, so we're going to go ahead and get started here. I will start today's webinar with just a few logistics. To ensure the best audio experience, all participants have been placed in silent mode, but if you have any issues or you have any questions, please enter them into the Q&A panel, excuse me, rather than the chat located on the right side of your screen. Today's webinar is being recorded. The recording will be posted to the NASA Earthdata website, as well as to our NASA Earthdata YouTube channel within a week of completion. Once completed, I will send an email to all registrants with the recording links and also a link to the presentation slide deck that's used in today's webinar. As far as timing is concerned, today's webinar will be 1 hour and long with 45 minutes allocated to the presentation and demonstrations and an additional 15 minutes for the question and answer period. We will have 2 speakers this afternoon. Our first speaker is Bruce Wilson. Bruce is the group leader for the Remote Sensing and Environmental Informatics within Oak Ridge National Laboratory Environmental Sciences Division and the manager of the NASA ORNL Distributed Active Archive Center, or ORNL DAAC. Our second speaker is Rupesh Shrestha, a research scientist at NASA ORNL DAAC, an adjunct assistant professor in the Department of Forestry, Wildlife, and Fisheries at the University of Tennessee, Knoxville. Bruce will begin this afternoon's webinar. Let me pull up the agenda slide here, with an introduction to the ORNL DAAC and also an overview of the JEDI mission and data sets. From there, he will speak to JEDI data discovery and data access services and provide a context for accessing these services within the Earthdata Cloud. From there, we will transition over to Rupesh for an in-depth description of JEDI Level 3 and JEDI Aboveground Biomass Density datasets at ORNL DAAC. And then finally, he will go through a series of data discovery and data access demonstrations. Once Rupesh is finished with his demonstrations, we will transition to an optional final set of polling questions. I will give these questions approximately 5 minutes or so before we transition to the Q&A session, but I will leave the questions open much longer for those of you who would like to provide feedback. And then from there, we'll transition directly to the Q&A period. Depending upon the volume of questions that are received, what we'll do is we'll extend the Q&A period an additional 15 minutes from end time for those of you who are able or who may wish to stay on the line, but we will have a hard cutoff of 3:15 p.m. And just one quick note about the Q&A period. We will try to answer all of the questions within the time allotted, but if we're not able to address your question during Q&A, our speakers will be able to follow up with you offline. With that, let me stop sharing my screen and toss the presenter role over to Rupesh, and then Bruce will kick us off here. So give me just one moment here. All right, so Rupesh, you should have presenter privileges in just one moment. Okay. Okay, so there we go. I was going to say currently we were on slide 15.
Perfect.
All right.
So thank you.
Thank you.
So hello, as Jennifer said, I'm Bruce Wilson, and I have the privilege of being the ORNL DAAC manager. We've talked about this briefly. I'm going to give an overview and context covering the ORNL DAAC, the Global Ecosystem Dynamics Investigation, or JEDI mission, and the services that we make available for JEDI data. As part of those services, I will touch on something called Earthdata Cloud. There have been some other webinars that have covered Earthdata Cloud, so I won't go into a lot of detail, but some context is important for what Rupesh will be covering. And once I've gone through that material, then Rupesh will provide more technical information about the JEDI data products. And he can go into how to access this using the Amazon Web Services S3 protocol, which is a way to bring your compute to the data. And he'll show how to use one of the Earthdata Cloud services called Harmony to subset that high resolution above ground biomass data. So we've mentioned the ORNL DAAC, and this is one of the 12 NASA Distributed Active Archive Centers, which are part of the larger Earth Observing System Data and Information System, or EOSDIS. Each of the 12 DACs has a particular focus area, and these are shown on this slide. And if you do an internet search for NASA DACs, you can find a lot more information about the DACs and EOSDIS. For JEDI, there are 2 DACs involved, and the links to these home pages are on this slide. The Land Processes DAC, or LPDAC, is located at Sioux Falls, South Dakota, at the USGS Earth Resources Observation and Sciences, or AROS facility. The ORNL DAC is at the Department of Energy's Oak Ridge National Laboratory, ORNL. And these 2 DACs each operate under interagency agreements between their respective agencies and NASA. And this is an example of some very effective long-term collaboration across the U.S. federal agencies. LPDAC and the ORNL DAC collaborate on JEDI data, with the lower level data available through LPDAC and the higher level data available through the ORNL DAC. And if you don't understand what I mean by data levels, hang in there a few minutes and I'll cover that when I walk through the JEDI data products. Focusing for a minute on the ORNL DAC, we are, more formally, as has been said, the Oak Ridge National Laboratory Distributed Active Archive Center for Biogeochemical Dynamics. Our focus area is supporting the NASA Terrestrial Ecology Program, and that work includes a lot of data from NASA field campaigns and airborne instruments. We do a lot of work to support site-based research, both making the data that they generate available to the public and helping them to access satellite remote sensing data. In this screenshot of our website, I've shown a highlight of the JEDI Level 4B above ground gridded biomass density product. And let's use that as a chance to take a step back and talk about JEDI and what we mean by these different levels. So, as I said earlier, JEDI is an acronym for the Global Ecosystem Dynamics Investigation. The JEDI sensor is a high-resolution LiDAR instrument geared to understanding forest structure. It was launched into the International Space Station in December 2018, and it completed its initial checkout in April of 2019. You'll hear us talk about mission weeks, and that's a measure of the time since the JEDI sensor was installed on the ISS. The instrument has 3 lasers that do full waveform LiDAR, working at the near-infrared, or NIR, region of the spectrum. And I'll have a bit more information about those lasers on my next slide, but they translate into 8 tracks, with these LiDAR shots having about a 25-meter footprint on the face of the Earth. Because of the ISS orbit, the JEDI data covers the region between about plus and minus 52 degrees latitude. That provides coverage for a lot of very important ecosystems, but it does mean that JEDI doesn't cover the boreal forests, as an example. And lastly, I've provided links to the website for the JEDI science team there at the University of Maryland. You can find a lot more information there. I've given the ORNL DAC's landing page for JEDI data, the JEDI landing page for the Land Processes DAC, and a link to an excellent YouTube video developed by our LPDAC colleagues. So, as I noted earlier, JEDI is a full waveform LiDAR instrument, and given the ISS orbit at something just over 400 kilometers, that beam has about a 25-meter footprint when it reaches the Earth, as depicted in the middle of this slide. The instrument then gets a measure of the number of photons reflected back as a function of time, which then gets translated into distance. And you'll hear us talk about shots or footprints, and that's the same thing. When we talk about that footprint level data, that's data that's extracted from each laser shot and represents that roughly 25-meter spot on the face of the Earth. As shown in the figure at right, these 3 lasers make measurements in a pattern that results in 8 beams or tracks along the Earth. Along any given beam, there's about 60 meters between each shot, and the beams are about 600 meters apart. So this means that each ISS pass is seeing just a small part of the area that it's going over, but the ISS makes a lot of passes, and JEDI is building up a more and more comprehensive picture based on this. So that waveform we've shown right, geolocated at each one of these shots along each one of these tracks, is that level 1 data product. So then the next step in the science team has developed algorithms that extract out different metrics from this waveform, such as where the ground return is located and different parameters reflecting the height of the things above the ground that are reflecting light. This analysis generates the level 2 data products, which are the elevation and height metrics, as well as the canopy cover and vertical profile metrics, again, at each shot along each track. More details can be found in the documentation for each of these data products and in something called the Algorithm Theoretical Basis Document, or ATBD. Having that data at the footprint level is really useful. But if someone wants to use it for building maps, using it in a model, or otherwise understanding the data at a landscape scale, it's very useful to have it on a regular grid. For these canopy structure metrics, the science team has taken that footprint level data and aggregated it, today using averaging, on a 1 kilometer grid, and that's the level 3 data product. To be a bit more specific, that grid is the Equal Area Scalable Earth, or EASE grid. And again, user guide and ATBD have more details. So returning back to the footprint level and the center part of this slide, what we're interested in here is biomass. So the science team has used a lot of calibration or ground truth data to build a set of models for how these canopy metrics translate into an estimate of above ground biomass. These different models are optimized for different ecosystems. And in the level 4A data, we use that footprint level metrics and use each of the models to build an estimate of above ground biomass for each shot, and then a very structured method to pick the best model for each footprint. That's that level 4A data product, footprint level estimated above ground biomass. And then finally, taking this footprint biomass estimate, we again have the need for gridded data, and that's the level 4B gridded above ground biomass estimate. And because the biomass estimate is subject to some errors, a simple averaging algorithm isn't the right answer. And again, Rupesh will have a bit more detail in his part of the talk, and a lot more detail is in the user guide and ATBD for the data product. So summarizing, this table shows the different data products available for the JEDI mission, along with which DAC is responsible for archiving and delivering that data. Our land processes DAC colleagues spoke about their work with JEDI a while back in a June 2020 Earthdata webinar. We'll have that link in chat. But before I move on to talking about the different services available for JEDI data archived at the ORNL DAAC, I need to take a bit of a side trip, and let's talk briefly about Earthdata Cloud. So Earthdata Cloud is a major initiative for the NASA Earth Science Data Systems Program. Our colleagues, for example, from the Global Hydrometeorology Resource Center DAC and Physical Oceanography DACs, or GHRC and PODAC, have spoken about Earthdata Cloud in 2 previous Earthdata webinars, and I do strongly recommend those. And I'm not going to go into a lot of detail here. But a key point about Earthdata Cloud is that it's an important tool in the NASA Earth Sciences and advancing open science. It's enabling cross-DAC collaboration, including collaboration on tools that work across DACs in ways that really weren't possible before. These common services are one way to let users get just the data that they need, and Rupesh is going to show some examples, and even if that data comes from different DACs, which we won't be covering today. So Earthdata Cloud, being built in the Amazon Web Services public cloud, also allows users to bring their compute to data. I'll comment that Earthdata Cloud is both a work in progress and something very much in use today. We're continuing to add capabilities and do that addition on a pretty rapid pace. So I mentioned this idea of tools that work across DACs, and I'm going to call out 3. The first is called Harmony, and you can find more at harmony.earthdata.nasa.gov. It's a common framework for a lot of data transformation services that include subsetting, variable selection, regridding. And Rupesh is going to show an example of how to use Harmony to subset that level for a high-resolution footprint level biomass data. For those who are familiar with OpenDAP, Earthdata Cloud includes an instance of the HIREC server, which works with most data that's in HDF5 or NetCDF format. We also have a tutorial for using that OpenDAP with the JEDI Level 4A data, but we won't be covering that tutorial today, but it's in the links that have been provided. Finally, as a tool for enabling science, almost all data in Earthdata Cloud is available for what's called direct S3 access. For those not familiar with S3 access, think of this as a way to let your virtual machines in AWS access the data files as if they were local to that virtual machine and at speeds that are just not possible for internet downloads. And while users will always be able to download the data for free, S3 access enables computing and analysis that is simply not practical with the traditional download and analyze mode of operation. So when you're looking at results in Earthdata Search, you can see an icon for Earthdata Cloud for each collection that's available in Earthdata Cloud, as shown in that screenshot at bottom left with the arrow pointing to it. And if you go into the collection details for a data set that's available in Earthdata Cloud, you can see instructions for which AWS region the data is in. Almost all of it is in US West 2, and instructions for how to access that data using S3. And again, Rupesh is going to be showing an example for how to do that as part of today's webinar. So now coming back to the JEDI data, this slide lists all of the different services that the ORNL DAAC makes available for the JEDI data. Because the data are in different formats, level 3 and 4B are in GeoTIFF, 4A is in HDF, the data are also used in different ways. There are different services available to do different things. You do need an Earthdata login account for each of these data access methods. If you don't have one, it just takes a few minutes to set this up. And this login is needed so that we can get some metrics on who's using the data, and so we can notify users if problems are identified. That did come into play earlier this year, actually for the JEDI data. A user working with Rupesh on one of these examples helped us to identify an error that was affecting a small fraction of the JEDI level 4A data. We got that info back to the science team, worked with them and published corrected data, and having that Earthdata login information allowed us to contact the users who had downloaded that JEDI 4A data and let them know that a corrected version was available. I'm not going to go into further details on these services. The slide deck link that's been posted has the slide in it, and each of the rows has a link that will either take you to the tool or the services or provides more information about using that tool or service. So with that, I want to turn this now over to Rupesh. I've highlighted the two services on this slide that he will be talking about more in his portion of the webinar. And thank you.
Thank you, Bruce. I'll first give a brief introduction of JEDI Level 3, Level 4A, and Level 4B data products and their algorithms. And then I'll show examples of accessing JEDI Level 4A dataset using two access methods, the direct S3 access and access via NASA Harmony API. At the end of the webinar, I will also demonstrate how to retrieve Level 4A subsets from a NASA Earthdata Search user interface using Harmony. So I want to reiterate what Bruce mentioned earlier about JEDI orbits, footprints, and grids. So that will give some perspective on how these products are derived. So the image here shows one full JEDI orbit. The JEDI footprint level files or granules are divided into suborbits. For example, this particular orbit has 4 suborbital granules for L4A. So the borders between two adjacent suborbits are indicated by red dots in the figure here. So this image shows JEDI orbits over a period of 1 day. So there are 58 suborbital granules for this particular day. And this image shows JEDI orbits over a period of 1 week. So there are 397 granules for this period. You can also see there are gaps over the oceans as JEDI suborbits over the water mass gas are not included. So over the last 3 years, JEDI has flown tens of thousands of orbits, collecting many billion shots and giving more and more coverages of the Earth's land surface. So this image shows a 1 kilometer by 1 kilometer east grid, which is the grading system used for the level 3 and level 4B products. So this particular grid is over Tasmania, Australia, so where some of the tallest trees in the world are located. So there are 10 JEDI suborbits that pass over this 1 kilometer by 1 kilometer grid, shown by the green lines here. So this image shows the JEDI shots from those 10 JEDI suborbital files. The yellow dots in this figure represent one JEDI shot or footprint, and there are a total of 193 shots in this grid. So I also want to point out that each sort is identified by a unique sort number as shown for this particular sort, shown as a red dot here. So JEDI level 3 provides a gridded land surface and canopy metrics. So it is derived from a JEDI level 2A footprints, so which in turn is derived from JEDI level 1B footprints. The JEDI level 1B provides a geolocated corrected waveform. So a waveform is shown here in the left for the same JEDI shot from the earlier slide. So at this level, we do not know yet where the ground and the canopy tops are. So for the JEDI level 2A, so additional algorithms for waveform interpretation are applied. And we now know where the canopy tops and the grounds are. So canopy is shown by the green dashed line here on the top, and the ground or the elevation of the lowest mode is shown by the red dashed line at the bottom here. Now also, we now have a relative height metrics. So the relative height metrics at 40th and 80th percentiles are shown in the figure with the green dotted lines. So JEDI L3 uses the relative height at 100 percentile or RH 100 and the elevation of the lowest mode. So it also uses additional L2A flags for shot editing. So L2A flags and the criteria are shown here. So in addition, digital elevation models from TAN-DEMX and NASA's SRTM are also used to further edit shots and orbits. In the second round of the shot editing, which is performed based on whether the SRTM and TAN-DEMX differ more than a threshold value, shown here in the table. So there are additional quality control applied, which is described in the ATBD in more detail, and the link to the ATBD is provided here. So currently, L3 grids are simple averages and the standard deviations of good quality shots. In the future, L3 will use more advanced interpolation techniques, such as thin plate splines. So all the JEDI level 3 data files are published as cloud optimized geotips, so which enable a more efficient workflow on the cloud, as well as it can be used in the traditional GIS systems. So it uses a 1 kilometer ease grid. So there are currently files covering 4 time period. So the most recent being from the mission week 19 to 162, which we only published this week. So mission weeks, like Bruce said earlier, starts on December 5, 2018, when the JEDI satellite was first launched. And there are a total of 5 variables available. So these are the available layer for the JEDI L3 product. The first one is the counts, which provides the number of JEDI shots that pass the QA process for each grid. So other layers includes the mean and standard deviation of the elevation of the lowest mode and the relative height at 100 percentile. So elevation of the lowest mode approximates the mean ground elevation, and the relative height 100 approximates the canopy height. So JEDI level 4A, which is a footprint level product, provides estimates of above ground biomass density at footprint level and their prediction interval. JEDI L4A uses 35 prediction strata defined by 5 plant functional types that are distributed across 7 world regions, shown on the left here. Across these prediction strata, simulated JEDI waveforms with co-located field data were used to create L4A AGBD models. So these simulated waveforms are essentially LVIS flights, which is a full waveform airborne lidar, a precursor to the JEDI instrument. So for each algorithm setting groups, which is a set of parameters used to detect waveform signals, the JEDI models are applied to estimate AGBD. So JEDI L4A dataset includes several quality flags. So more details are available in this ATBD as well as in this manuscript by Duncanson and others. So JEDI L4A datasets are available as a SDF5 format. So there are 180 plus variables within each of the 8 beams, so resulting in almost 1,500 variables in each file. So here is a list of some variables of interest. AGBD, or above ground biomass density, and its upper and lower prediction interval, the prediction stratum of the sort, and the quality flags. So please refer to the dataset user guide and this tutorial for more information about data structure and other variables included in JEDI Level 4A. JEDI Level 4B provides gridded mean above ground biomass density, or AGBD, and JEDI Level 4B uses a hybrid method to estimate the mean AGBD for each grid. So that means it can compute uncertainties due to how JEDI samples the grid, as well as the uncertainty due to JEDI L4A AGBD models. So this approach is described in detail in this publication by Patterson and others. So since at least 2 clusters are required to calculate variance under hybrid estimation, so it needs at least 2 intersecting ground tracks within the grid to apply the algorithm. So at the end of the mission, the grids without a sufficient number of clusters will be estimated using a generalized hierarchical model. So this is also described in the ATBD, and the links are provided here. Like JEDI Level 3 gridded products, JEDI Level 4B files are also cloud optimized GOT files in the same 1 kilometer east grid system. So there are 10 layers available within JEDI Level 4B dataset. So mean AGBD estimates and standard error for 1 kilometer grids are provided. So variance component 1 indicates uncertainty due to field to JEDI model used in L4A, and variance component 2 indicates uncertainty due to JEDI's irregular sampling within the grid. So quality flag is also provided. So quality flag of 2 indicates that the grid has standard error of less than 20% or 20 mg per hectare, which is the JEDI mission requirement. So currently we have some grid cells that do not yet meet these requirements, but some of them will do in the future as more JEDI sorts are collected. So ORNL DAAC has developed a set of Python Jupyter notebooks to access, subset, and visualize JEDI datasets using various methods. Some tutorials also have associated scripts available, so which makes it easier to run the script directly from the command line. The tutorials and the scripts are all available at this GitHub page. Now I'll go and demonstrate 2 of the methods to access JEDI Level 4A dataset. So this is the first tutorial we'll go through together. So this tutorial is also available at this GitHub link shown here. So in this tutorial, we'll retrieve L4A dataset from Earthdata Cloud using direct S3 access. To be able to access NASA Earthdata via direct S3 access, you'll need to set up the AWS instance in US West 2 region. So NASA has developed these primers and tutorials, which will provide a good resource if you are new to the cloud. So to run the Jupyter Notebook from AWS EC2 instance, there are several ways to do it. So one of the way is shown here. First, start the Jupyter Notebook on port 888 with a no browser parameter. And on your local machine, you can forward the port 8000 to 8888 like so here. And now the Jupyter Notebook will be available at the HTTP localhost 8000 in your local browser. So Earthdata login is required to obtain S3 temporary credentials and for S3 direct access. So you can set up .NET-RC file in your AWS EC2 instance. So you can refer to this instruction here on how to set up that .NET-RC file. So let's first import Python modules. So most of these are common Python modules, probably except for some modules. So if you have a module not installed, you can install using pip3 install command like shown here. So you can also use conda if that is your preferred way to manage Python modules. So here we will be using S3FS module, so which is a Python interface for file system like access of the S3 objects. So we can also use other modules such as Boto3, which is another alternative for S3 direct access from Python. So the Harvard Forest is one of the most extensively studied ecological sites in the United States. So in this tutorial, we'll be retrieving selected JEDI L4A variables within the bounds of the Harvard Forest. An area within the Harvard Forest is provided as a GeoJSON file in the polygons folder. So here, we are reading the GeoJSON file and organizing the coordinates in a proper orientation and plotting over a base map. So here we are defining a function that searches for especially overlapping JEDI L4A granules. So we'll be using NASA's common metadata repository or CMR API to search and find the L4A granules. So this function search CMR takes two parameters, dataset DOI and a GeoJSON object. So here first we pass the DOI of the JEDI L4A to get the concept ID. So the concept ID is the NASA's unique identifier for dataset. CMR can only query 2,000 granules at a time currently. So we'll page through the API response with a while loop. And here we are defining the CMR parameters. So it is also a good idea to specify simplify shape to true, as a CMR currently has limits to the number of coordinates it can support for a polygon. So here we are defining the CMR parameters. And then now we are submitting a CMR request. And if we get a valid response, we'll loop through each granules and append S3 links to the S3 array. So here, first we define the DOI for JEDI L4A, and we also define a GeoJSON object for the bounding geometry and pass these through the search CMR function. The function will return a list of S3 granule links. The links will all start with S3://, and we can print the first of the two items from the list here. So here we are plotting the distribution of monthly JEDI L4A granules over the Harvard Forest, so that we retrieved in the previous step. So as you can see, some months do not have JEDI granules, with some months have up to 5 granules currently. Temporary credential is required for S3 direct access on the Earthdata Cloud. So each of the NASA's DAC has its own endpoint. So more information on how to obtain a S3 credential for ORNL DAAC is provided in this link. So these credentials are temporary, and currently they are valid for 1 hour only. So here we define a Python function to retrieve the S3 credential for the ORNL DAC and print the expiration date. So once we have the S3 credentials, then we can pass them to the S3FS class called S3 file system. So it needs 3 parameters: the key, secret, and token. For this tutorial, we'll be retrieving 2 AGBD variables, AGBD and L4 quality flag, defined here. In addition, we can also retrieve other ancillary variables that provide geolocation, like lat lowest mode, long lowest mode, elevation, and a shot identifier. And we'll save them as a CSV file. So here, once we open the S3 URL with the S3FS file system defined in the previous step, so we can read the JEDI L4A file using HPy Python module. So first, we will read the latitudes and longitudes of all the shots within the beam, and then find the indices of the shots that are within the Harvard Forest boundary. Then we'll retrieve all the variables of interest only for the shots that are within the Harvard Forest boundary and save them as a CSV file here. So this step might take some time to complete depending on how big the bounding area is. So once that is complete, then now we can read the CSV file that we just downloaded into a pandas data frame and plot the Aboveground biomass density values on a map. So the AGVD ranges up to 400 mg per hectare for the harvest forest area, as you can see here. So you can now use this subset JEDI L4A for further analysis in your workflow. So this ends our first Jupyter Notebook tutorial. So this is the second tutorial that I'll be showing. So this tutorial is also available at the GitHub link shown here. So in this tutorial, we will use a NASA Harmony API to access and subset JEDI L4A datasets. So NASA Harmony API, like Bruce said before, brings Harmony to disparate datasets in that it allows seamless access of NASA dataset from different DACs in analysis-ready form. So as Bruce pointed out earlier, it has capability for subsetting, regridding, and reprojection. So in this tutorial, we will be downloading JEDI L4A shots that are within the bounds of an area in NASA's Delta X project. The Delta X project collects field and airborne measurements of ecologic and hydrology variables over the Mississippi River Delta of the United States. The Delta X projects includes data sets of the field measured above ground biomass. So at the first step, let's first import all the required modules. So we'll be using Harmony Python modules here, as the Harmony API is the REST-based API. So it can also be accessed directly via HTTPS GET request without using a module, but Harmony Py just makes it easier as it incorporates NASA Earthdata login, CMR API, and Harmony API into a single package. So now let's initialize Harmony Py's client. With the client, we can pass our Earthdata login authentication if we want to, like so. We can also rely on the netrc file, that we already have set up in our system when downloading other NASA datasets. So Harmony API needs the dataset concept ID, so which is the CMR's unique identifier for the dataset that we used earlier. So we'll retrieve the concept ID for L4A by passing a DOI of the dataset, as we did in the previous tutorial. So now with the concept ID, we create a Harmony collection object here. And we'll also define JEDI L4A variables of interest. For this tutorial, we are only interested in these variables from a single beam. And we'll also define the temporal range. So Harmony needs the time range to be defined in this particular way with the start and the stop date times written as so. The locations of the Delta X above ground biomass plots is saved in this GeoJSON file. Let's open it using GeoPandas and compute its bounds and define the Harmony's bounding box, like so here. So which needs to be defined in a specific way with west, south, and east and north coordinates specified. And so here we are plotting the locations of Delta X biomass plots over a base map. Now let's create a Harmony request with the parameters we defined earlier. Harmony request needs a collection variables earlier, Harmony interest and temporal range and spatial bounds. So you can also provide a polygon, a GeoJSON file instead of a bounding box if you have one. So once this request is created, we can submit the request using the Harmony client object. So it will return a unique job ID, so which we can use to check the status of the order. The status of order will be shown as a progress bar. So we'll be using a download all, which is a built-in multi-thread downloader for a fast asynchronous download of all the subset files. That means that files are downloaded as soon as the subset files are created. So all the subset files will have a underscore subsetted that h5 suffix. So once the files are downloaded, we can now open these files into a pandas as a table. So here we are printing the top few rows of the table. And now here we are plotting the above data frame into a map using GeoPandas. So we can save the pandas data frame into various formats such as CSV and GeoJSON and use them for further analysis. So this ends our second Jupyter Notebook tutorial. The Harmony API is also available via a graphical user interface from NASA Earthdata Search at this URL, search.earthdata.nasa.gov. Now I will show how to submit a subset request for a JEDI L4A from Earthdata Search interface using Harmony. First, let's search for JEDI L4A. So in the collection list here, you'll see this button for the collection that supports customization, such as spatial subsetting, temporal subsetting, and variable subsetting. So let's click on the JEDI L4A collection. So we'll see there are 52,000 granules returned, which are the total granules published so far. Now we can provide a temporal extent to the search criteria. So let's say we are interested for the month of February 2020. And now we see that there are a total of 1582 granules for this month. So now we can define an area of interest by clicking on this button here. So we can define as polygon or rectangle or even upload files such as KML, GeoJSON, and other supported formats. So let's say we are interested for JEDI L4A dataset for Madagascar. So let's draw a boundary polygon around Madagascar. And by doing so, we have filtered the total number of granules down to 32, as shown by the red arrow here. Now let's click the download all button, the green button on the bottom. So it'll display these options now. So here in the first option, instead of direct downloading the full 32 granules, let's select a customize option, so which is essentially the Harmony subsetting feature. So in the second option here, you can configure data customization. So we already did temporary subsetting, so only variable subsetting is available. So let's click on this blue edit variable button. So now we can select the variables of interest. So all of the JEDI L4A variables across 8 beams are available to select here. So once we select the variables we are interested in, so we can click the download data button. So it will now show the download status of your order. So as you can notice, the access method here says Harmony. So once the process is finished, you'll also get an email notification. So this is how the page will look like when the job is completed successfully. The links to the subset files will be displayed in the list here, so which you can use to download the subset files. So which would be much smaller than the original L4A suborbit granules, depending on your bounding box. So this completes our presentation. So I'll now pass it to Jennifer for the questions and answer session. Thank you.
Okay, thank you very much, Rupesh. At this point, why don't I go ahead and open the final set of polling questions for everybody. We'll give these about 5 minutes or so, and then we'll transition to the Q&A. But again, I'll leave them open much longer, so you have time to weigh in a little bit later. All right, and let's go ahead and open those polls. And I just wanted to stress again to all participants that I will be sending a link to the recording within a few days of completion. There's just a bit of post-processing that needs to take place. In that email, I will also include a link to the presentation slide deck, and I'll include many of the links that are also embedded within the slide deck on our NASA Earthdata YouTube channel when it's posted there. So it'll be posted to our earthdata.nasa.gov site. I'll send an email, and you can also find it on our YouTube channel as well. All right, we'll give these like 3 more minutes, and then we'll transition to Q&A. Okay, everybody, why don't we go ahead and transition to the Q&A session. Again, the polls will be open for another just shy of 45 minutes, so I am going to try to capture those questions that were asked within the chat, and then we'll move along really quickly to the Q&A panel questions. Okay, let's see here. Okay, so one of the first sets of questions for our speakers are the calibration analyses and results published?
Yes. So if you look at the Laura's paper, the Duncanson et al., which was published last year, so it has more details on it. So,
Okay, great.
So all of all of the models are not publicly available yet, but in future it will. But that paper details like how each of the models for each of the prediction stratum was calculated.
Okay, great. And again, these links are contained within the presentation slide deck, and I've included the link a few times, but I'm happy to do so again if necessary. The next question from the same participant is a map of the calibration points available. Are the data available? Again, getting back to the calibration analysis, and perhaps that's covered within the paper.
Yes, the map is available, but the data is not yet available.
Okay, thank you. The final question, what is the return time for precise shot locations?
What do you mean by return time? So how long it takes from the instrument that I shot to return back to the instrument?
That would be my interpretation, but if this participant would like to provide further clarification, that might be helpful. All right, why don't we move on to the next question? What is the lowest canopy height distinguishable from the ground? Is independent data incorporated to verify the ground level?
So independent data is the DEM for the level 3 data sets. So if you look at the ATPD of level 2A, you'll find more details on how that was done.
Okay, and then I think Bruce may have answered this question earlier, although we were speaking to tutorials in R. Are there any APIs for R? Or is it just for Python?
The APIs are language independent. So we've shown some examples of how to access those APIs from Python, which is the language that Rupesh knows best. But taking into account some of the comments that some others have made, you can use R or any other programming language of choice to access the APIs.
Thank you very much, Bruce, and thank you, Rupesh. Let's see here. I think some of these questions you had addressed, whether or not the data are available in Google Earth Engine. My apologies. That was quite a mouthful. Bruce had addressed that already, as well as Rupesh. I'm just moving on. Let's see here. To those that were not answered previously. Okay. Okay, so looks like then the next question will be, does JEDI have the capacity to characterize the biomass components, aquatic and airborne species excluded?
So this question is about if JEDI can model the component biomass, like leaf biomass, stem biomass, and the other root biomass. So if you have a field-based model that you have developed, then it's possible as long as you are willing to do the work. But level 4A dataset does not provide that. But if you want to use your own model, so you would be able to use a level 2A dataset and then use the metrics available there, and then you would be able to apply their own model to the data set. But it depends on if you already have that kind of model that can provide estimates of component biomass.
Okay, thank you very much, Rupesh. The next question is, what is the positional accuracy of the footprints?
Okay, so it varies from, I think, 10 to 20 meter for horizontal accuracy, and I'm not sure about how much it varies for the vertical accuracy. I think it's in order of 10 meter, probably.
And that is one of the things that's being improved with each version of the JEDI data. We're on version 2 now, version 3 being expected later this year.
Yes.
Okay, thank you both very much. The next question is, can the same data for AGBD be analyzed using ArcGIS software?
Yes. So if you want to use L4A dataset, the easiest way would be to convert that into a GeoJSON, and then ArcGIS can take it. For L4B gridded biomass, the ArcGIS can directly read the GeoTIFF file. So it will be possible.
Great, thank you so much. The next question is, I was wondering if there will be a gridded leaf area index product, level 3. It says so on the JEDI homepage, but I couldn't find it in the ATB or data.
Yes, so they don't plan to release it in future. So that question came up earlier a few months ago. A user asked, and so I reached out to the science team, and they don't have immediate plans to release gridded LAI product. But gridded product you can derive by yourself from level 2B if you are interested on.
Okay, thank you very much.
Level 2B is a footprint level data.
Wonderful. Thank you very much, Rupesh. The next question is, we use so let me get to the comment part first, and then the question. We use terrestrial laser scanner to measure the forest with the same as JEDI footprint, and could get some plots exactly at JEDI shots located in Asia. Now we want to compare our field above ground biomass with level 4A AGBD data for the particular shots. So how can we compare field biomass with JEDI biomass? Is there an algorithm used by JEDI which we can also use for field AGB calculation?
So first thing is like the shots that I mentioned with the JEDI shots have an offset. Like, so if you have to make sure that that shot you are seeing is exactly over your field plot or not. So if you read the Duncanson paper, so it goes into detail on how they have computed the terrestrial derived model and then applied it to the LV's simulated data set. So you would be able to follow their methods in detail, and then you'll be able to come up and apply your own model. And there is also a tutorial in our GitHub page, so that shows how to apply AGBD model for the L2A dataset. So if you have a model already, so you can use that tutorial and then apply your own model to get the above ground biomass estimate.
Okay, thank you so much. The next question is there a subsetter to combine the model data parameters and coefficients used to create the AGBD for the pulse?
Subsetter?
Yes, so is there a subsetter to combine the model data parameters and coefficients used to create the AGBD for the pulse?
So those coefficients are always same for all the files, right? So you don't even need to subset it. So if you download one from the file, then you'd be able to use that, because those are very small set of files. So they only probably is in kilobytes. So they are not a big file. So probably you won't be needing a subsetting for that. But if you use a harmony subsetting, so you'll get all those parameters in addition to the beam dataset. So if you order a beam, and if you order a variables within a beam, you'll also get the metadata as well as the ancillary variables where all the model coefficients are also provided. So if you order from the harmony, yes.
Okay, thank you very much. And just we're getting close to the extended Q&A here. If we do not get to your question, I see that there's additional feedback within the chat, but I can't track that simultaneously. So if my backup host could take a look at that. Let's move on to the questions in the Q&A, continue forth rather. The next question is, JEDI 2A in Google Earth Engine has two quality flags, degraded and quality. Can someone give further details about their meaning or intended use?
This question is about 2A.
Yeah, that might be a question. Isn't that LPDAC data?
Yes. So those are the yeah. So if you look at the user guide, so and ATPD, so all those information about the flags are provided. So I suggest that like you start with the user guide first, and if the information is not there, and read the ATPD.
Yeah, and I think too, Jonathan, I can follow up with a point of contact at the LP DAC and just get back to you offline, connect the two of you for a follow-up on that question. All right, the next question is there a possibility to use JEDI biomass estimate to investigate plant litter input to the ground? So there's two parts. Is there a possibility to use JEDI biomass estimate to investigate plant litter input to the ground, part one? And then the second piece is, are the data precise enough to get an estimate of litter input?
So I would say that JEDI cannot probably not detect the plant litter. So probably people have done that kind of work with the airborne lidar and terrestrial lidar. So that's it. So I would say that is a kind of research questions like you would be able to investigate. But I'm not aware of any work that has been done on that front using JEDI.
Okay, thank you so much. I appreciate it, Rupesh. The next question is, let's see here. Is the level 3B and level 4B gridded data available on a monthly basis, or is it an average over the JEDI data collection period? Oh, excuse me. Bruce has answered that. My apologies, everybody. Let's move on to the next question. What's coming in the next years for JEDI? How long will JEDI remain operational? What are current plans for the next instrument, coverage, etc.? So what's coming
Bruce,
next for JEDI? How long will JEDI remain operational? And what are current plans for the next instrument or coverage?
So my understanding is that the JEDI mission has been extended through January 2023. That's based on the most recent data on Earth Observation Portal. And as for plans after that, I think I want to take that as a follow-up question to address with the users.
Okay, thanks so much, Bruce. The next question is, I appreciate the feedback too. I know that one of the users has put some feedback in there about building an R package for downloading and processing JEDI level 4A data. So that's great that you've shared that. Thanks so much. The next question is there a data set that could be layered on top of 2A data to convert to 4A? 2A data is available in Google Earth Engine, eliminating the large hurdles of processing and storing huge amounts of data when working on a global scale. If this isn't possible, is NASA lobbying Google to have this data added to GEE?
So I think I'd have to answer, part of the question is why, if the 4A data is already available. The algorithms for going to 4A, Rupesh has covered some of those in a different JEDI tutorial. Google Earth Engine is welcome to load data, but we're dealing with various different companies in those questions. So the algorithms are out there, but I don't think they've necessarily been built into packages. And again, the 4A data is available, and you can subset to get just the regions of interest, as Rupesh has shown.
Okay, thank you, Bruce. Moving on. Just want to make sure there are actually quite a few. Is there a way to test different results using the different ground finding algorithms? There are a few issues when estimating metrics in high sloped areas.
yes. So if you look at level 2A dataset, so they will give you 6 different algorithms that they have used, right? So they use different parameters to detect those ground points. So if the one algorithm is not working for you, you can check if the other algorithms might work better for you. So it depends on area to area. So if you investigate a little further and look into the 6 different algorithm groups that you have in level 2A products. So you'll be able to find the one that will work for you. And sometimes not all of the 6 might not even work, right? So if you're looking into a difficult terrain, probably there might be some issues. So that's my answer.
Okay, well, thank you very much. Let's see here. Just want to make sure that. Okay, are there opportunities to contribute to the ATBD validation or calibration through field AGBD data?
I think one way to do that would be to reach out to Laura Duncanson, Dr. Duncanson at UMD, or if you want to reach out to us, particularly through something like Earthdata Forum, or through the Contact Us at the ORNL DAAC page on the dac.ornl.gov, we can help to broker that conversation if you're not comfortable approaching them directly.
Okay, and so the forum URL, which I'll place in the chat and afterward here, is forum.earthdata.nasa.gov. The next question is, let's see here. Thank you, Bruce. Concerning the rate of coverage, I'm working at high latitudes at present. Where is the information that you mentioned published coverage at various time periods?
So what I was suggesting is one way to look at that coverage is that in the level 3 data, for example, that's giving you the number of counts. And so today, the level 3 data is published over 4 different time periods, and I don't have them off the top of my head, but they start at mission week 19 through mission week, whatever. You can look and see in any given grid cell how the number of counts is increasing over time. Or the other approach, again, using, for example, the subsetting approach with the level 4A data, or you could do it with the level 2A data. You can get the shots that are in your region of interest, and one of the fields there is delta time, which is giving you seconds for that shot since 1 January 2018. And so an animation of that would show you how the number of shots and where those shots are within your specific region of interest.
Okay, thank you, Bruce. There are a couple of questions that were kind of partially addressed earlier. Let's see here. So I'm going to move on. Let's see here. Could you briefly summarize the differences between the levels? For instance, you mentioned level 2 against level 4. Is there a resolution that is it the resolution that is the main difference between the levels?
No, the difference, NASA generally classifies level 4 as being model data. And so going from level 2 to level 4, there's a model that's been applied. But structurally, the level 4A data is identical to the level 2 data. It's a one-to-one map for the shots that are in the level 2A data to the level 4A data. And likewise, structurally, the level 4B data is equivalent to the level 3 data. It's just exactly what's the data here. The level 4 is a model output, and that model is how to transform the metrics into biomass and then how to aggregate that footprint level biomass into a gridded biomass.
Okay, thank you, Bruce. And I think the next question was addressed, but in terms of how accurate is the JEDI biomass estimation, I think Rupesh provided some accuracy estimates, and then you followed up by saying that the accuracy is being improved with each of the different and newer versions that come out. Do I have it right?
And also in the slide deck, there is a link to a new paper from Ralph Dubaya et al. In the slide where I put the L4B product. So if you look at that paper, it goes into detail on how accurate JEDI biomass estimates are. So it also compares JEDI biomass estimates with FAO biomass estimates, and also with the USDA Forest Service biomass estimates. So please refer to that paper in the slide deck.
That sounds great. Thank you so much. And then the next question is, for the level 4A data, shots which have a 0 quality flag, can we consider those values, or is it of no use for biomass?
Those quality flags are identified by the L4A algorithm that they are of the poor quality, right? So probably it would be a good idea to investigate further. So some people have like not use the quality flag, but instead use the sensitivity of each shot, and then try to filter it that way, so that they will get more shots. So if you apply if you get rid of all the L4A shots that have a quality flag of 0, then you probably might end up with a lot fewer shots than you would want to. So it depends on your needs. So that's the kind of like a standard flag that JEDI L4A algorithms has applied. So that means that the science team wants, if he wants to use it with caution. Like, as long as you know what you are doing, I think you can use it.
Okay, thanks very much. We've got about 4 minutes remaining in the Q&A session. Would it be possible or recommended to use JEDI data to derive large-scale DTM?
Can you repeat the question?
Sure. Would it be possible or recommended to use JEDI data to derive large-scale DTM?
Yes. So JEDI level 3 provides a DTM at 1 kilometer grid. So if that resolution is good enough for you, so it is found to be very. So they have compared level 3 grids, the elevation value with Tandem X, as well as NASA's SRTM, and they have found very good results. So you might want to check the ATBT of level 3 gridded products.
Thank you, Rupesh. The next question is, if version 2 horizontal accuracy is 10 meters, then is it necessary to run waveform collocation to validate JEDI AGBD versus on-the-ground measurement?
Yeah, that would be one approach to identify the shots, if they are falling into the same or not. So sometimes, there are the crossing. So if your site has a crossing of the JEDI orbits, like if there is a multiple shots from different orbits landing in your field area, then you might want to check those crossing from the different orbits. So that would be a good approach to use. But so other than looking at the waveform, I don't know there is other way to identify how much the horizontally it has shifted.
Okay, so the next question is, if you're interested in canopy structure, is there a product level you would recommend?
So L2A would be a good product that provides all the canopy structure at different relative heights.
Yep, thank you. And you know what? I will put a link to the LPDAC JEDI product table in the chat in just a couple minutes here. Speaking of the chat, let me go back and revisit this just to see, because I've been seeing that that it's active, but the question is, okay, could you send the link to the R package of the level 4A data for subsetting and download? Was that mentioned? This was mentioned a little bit earlier. So there are R packages. There are tutorials available at LPDAC, what I mentioned, for their lower level products. I would have to have Bruce or Rupesh speak to any R packages. Or did you mention it,
one
Bruce?
of the participants mentioned that they were developing an R package, and if they're interested in others taking a look at that, I'd encourage them to post the appropriate link for that in the Earthdata forum, again, forum.earthdata.nasa.gov, and that's one way of potentially engaging the community. If things have reached a point where someone is comfortable putting out a community-supported R package and having us point to them, we can do that through our learning resources. But today, I don't have anything that I'm specifically aware of as an R package for subsetting the 4A data. All we've put out so far is Python.
Okay. Okay, very good. Thank you, Bruce. Let's see, the next question, and probably the last question here because we're at our time limit, is the data available for a large watershed as full coverage or just as patches based on the travel path only?
Yes. So I would say, so there will be some gaps on the data set. So because JEDI is like a sampling kind of lidar, so it will fly and you will still have some gaps in the data set. Even if you look at the 1 kilometer by 1 kilometer grid, both level 3 and level 4B products, you'll see there are a lot of the grids that has no data values. So so depending on how big your water set is, there might be some gaps. But JEDI is a sampling lidar, so it will provide you a good sample of the data set across your watershed area.
Okay, thank you very much. At this point, we are going to wrap up our Q&A session for this afternoon's webinar. I would like to take a moment to thank our speakers, Rupesh and Bruce, for their time today, and to thank all of you for your participation. What I will do now is we will log off from the audio component. However, we will leave the virtual meeting space open an additional 10 minutes. And the polling questions are still open. If you would like to provide feedback, we certainly do appreciate that feedback. It helps to guide future webinars. It's really important. It helps us, address, any gaps in what we're able to provide and user needs. So thank you so much, everybody. Our next webinar will focus on physical oceanography data, and you can check earthdata.nasa.gov on the webinars page within the coming days for additional information. All right, so there are not any final comments from Bruce or Rupesh. We can say goodbye to everybody, and we hope to see you at an upcoming webinar. All right, thanks so much, everybody. Goodbye now.